Welcome back to UBC CS 532W. This is lecture 17 in graduate level probabilistic programming. We're going to talk about evaluation-based higher order probabilistic programming language inference today, including one more time sequential Monte Carlo. So I guess it's actually technically now lecture 14 to 16 recap. We talked about what is the higher order probabilistic programming language. We talked about function applications in FN. And we said that, if you use Pyro or PyProb or whatever, or you want to implement those, the language features in the model specification language are such that they become equivalent to the HOPPL. So like dealing with the HOPPL stuff is something that you have to deal with in those languages. In particular, you have to deal with an unbounded random variable cardinality, which means you can't unroll the graphical model, the program into a graphical model. You can't tell in advance whether or not a program is a HOPPL or a FOPPL, because you basically, in order to figure out whether or not a HOPPL program is a FOPPL such that you can unroll the graphical model, you have to effectively solve the halting problem, which you can't do in general. You could just try and fail, but that's a kind of a nasty way to write a compiler. Anyway, or evaluator. We've talked a little bit about addressing, in particular that addressing is required for some algorithms, and it's required in different ways for sequential Monte Carlo and lightweight Metropolis Hastings. We've talked a little bit about continuation or forking, that being desirable. In fact, it's a requirement, one of the two. And of course, you can use standard language compilers when you have continuation passing style stuff, which is pretty cool. And we've done SMC in general, but not necessarily so carefully focused on the Prob Prog part of the story. So today we'll be a little bit more relaxed. We'll just sort of cover at a high level some of the higher order probabilistic programming language inference algorithms. We'll do important sampling. We'll just review and return to lightweight Metropolis Hastings, and we'll review and return to sequential Monte Carlo. And I'll point out a couple of more advanced sequential Monte Carlo algorithms that are pretty cool that you might become interested in if you catch the sequential Monte Carlo bug, as it were. So we're going to use this intuitive sketch notation today rather than the book notation. I think at this point it should be relatively straightforward what's going on. We know that an evaluation of the program, in particular any of them, an evaluation results in some unnormalized joint distribution, which we'll denote by gamma, which is an expression or whatever, a sequence of sample and observe statements that make up the joint probability of all the random variable assignments and the observations on one particular trace of the program. And note that this very simple state space style notation hides a very complex branching dependency structure, but still really we're still talking about sort of state space models. In other words, when you look at what's at this style notation for HOPPL programs, what really we're saying is that there are a number of sample statements and then an observe, and we'll call out, and I will do this very explicitly when we do sequential Monte Carlo, we'll call out these groupings of latent variables with bold symbols and lowercase symbols for the underlying random variables. And yeah, so basically we're going to use cross here for concatenation to basically turn it into a vector. The reason why we use cross instead of just a vector is that these x's themselves can be, who knows, vector valued or string valued or something like that. So we have the joint the unnormalized probability we're after is the joint probability, and this complex dependency branching structure really is all about the fact that the link function for the ith random variable, where in even the yeah, this particular index may change depending on the trace. Anyway, so when we run the program, there's a link function that's computed from the entire execution state. Some non-trivial, basically, if you think about it, this is basically some sort of eval function here, actually, that generates the parameters for the sample. And this you can think of as the random variables generated, the random variable values generated on this one particular execution path of the program, plus any deterministic computation that also takes place using those values. That means that the type of the distribution can, of course, be a function of that, right? Of again, this set of latent random variables, so on and so forth. And in fact, technically, this should be a function of x's as well, and this should be a function of x's as well. So the point is, we can think of a probabilistic program in trace space as being a Markov model where the latent space is growing over time, and it consists of the evaluator state as you're going. Okay. Hopefully that makes sense. Okay. So in this context, we can sort of high-level overview what's going on in 3 different HOPPL inference algorithms, and this should be almost a review, so we might even run short today, which I think would be good for everyone. We'll talk about likelihood weighting, in other words, important sampling from the prior, Metropolis Hastings in the form of lightweight Metropolis Hastings and sequential Monte Carlo. So in the HOPPL context, how does likelihood weighting look like? It looks like what you would expect. Effectively, you run k independent copies of the program, simulating from the prior. So the way we would indicate simulating from the prior is just to write q of xk is equal to the prior distribution in the notation from before, where the parameters are deterministically computed from all the latent variables up to that point, so on and so forth. So yeah, then what do we do? At observed checkpoints, we accumulate unnormalized weights, the likelihoods, right? So for the kth particle, you evaluate the joint distribution over the proposal, which at the end of the day, after the entire execution of the program, is just going to be the product of the likelihoods. And you use these in approximate Monte Carlo integration. So basically, at the end of the day, when you write eval, your observed statement will compute this side effect at every observed statement encountered. That make sense?
Can I ask a question about that?
Yes, please. Yeah.
I mean, the HOPPL allows us to have traces that have different numbers of observed statements in there, right?
That's correct.
And this is totally fine with importance or with likelihood weighting, but it does seem that the programs that have more observed statements, they will always have a lower weight than the program. Oh, well, they will very likely have a lower weight than the programs with less observed statements.
Correct.
Is there some sort of meaning behind that, or is that that's just how it works? Maybe it's not an interesting observation at all, but
you can very easily confuse yourself about when or why you would use conditional observation. One place in which it is sensible is when you have a large model in which you have partial or semi-supervision, and you want to indicate whether or not you actually have data available in a data matrix in that particular entry or not. Right? If you're doing matrix factorization or something like that, and you either do or do not have data available, then you might make a conditional observe. In that particular case, you have the same number. You will almost certainly have the same number of observations per trace, no matter what. So making observe available to be conditional is a very useful thing from just a practical modeling perspective. When you start thinking about condition, like truly conditional observes, you start thinking, you get into the headspace where you're thinking about model selection, right? And there's some papers that came out of Galois back in the day, and we did. I would, this is a good question. I'm not prepared to answer it, but if I thought about it, I probably could. I believe that at the end of the day, everything works out, and you can formulate like model selection over a discrete set of models. Let's say, for instance, have let me. I think the safer thing to say here is the truth, which is that it is a language facility that's very useful for semi-supervision in large models. And when you have the exact same number of observes in all traces, then things are totally fine. It gets very confusing and very difficult to reason about when you have different numbers of observes per trace. But it is indeed allowed. And of course, the sort of geometric prior on that you're talking about, like the likely strong penalty for more observations is something that you'd have to think about when you're using the facility, for sure. The reason I'm trying to think of back in the day, we had a couple of examples where we wanted to use this, and I thought model selection was one, but then I started thinking about it, and I don't think that's true. I'll have to come back to this if it becomes important. Procedurally, everybody could do this, no problem. I mean, it's exactly the same thing in the HOPPL as it is in the FOPPL, basically, right? You just you hit the observes, and so be it that you happen to be in this context where you can't unroll the program, but you've already written an evaluating an interpreter, so this is fine. In a schematic sense, it's I sort of think about it this way, in that we have your evaluator running along, and I really think of both the sample and observe special forms as stepping out of standard program evaluation so that you can compute side effects or do other things to affect the way the program is run. So when you see these diagrams, you see this as sort of a dividing line, and you can think of what you see down here is either the evaluation of either a sample or an observed statement. Then at the end of the day, what likelihood weighting is doing is it allows you to run the program over and over and over again. And every time you hit an observe or a sample special form, you step out of the standard evaluator and do something such that when the program returns, you return the return value of the program, but also an associated weight. In these particular cases, unnormalized weights that you then have to normalize at the end when you finish running however many samples you run. Okay. This diagram makes sense. We're going to see a few of these diagrams today. Okay. Sorry, when I'm low energy and then I see and then I put in low energy, it feels even more low energy for me. So I need some energy today. Anywho, it's been a day of very high ups and very, very low downs already. So, okay, so we can do Metropolis Hastings as well. Single site Metropolis Hastings or lightweight Metropolis Hastings, they're all the same sort of name. So here we can do the same thing. We still have oops, excuse me. We still have the joint distribution as described. We have a normalization constant here that's missing. That's fine. And we know Metropolis Hastings at this point by heart. So we can just always plug in the joint distribution, i.e. we can put a trace in here on the top and bottom. So this would be a new trace and this would be an old trace. And we can sample in the space of probabilistic programming posteriors by modifying a trace to make a new trace, evaluating the joint probability, and go. There's Metropolis Hastings pretty much straight away, right? But what we need is a proposal distribution to get to the new trace from the old trace and the old trace from the new trace, right? This is just Metropolis Hastings, as you know. So we need a proposal. We've already talked about this, but here's an even simpler way of thinking about what the lightweight Metropolis Hastings proposal looks like, which is to get from the current sampled trace to a new trace, you just pick one of the random variable sites in the trace. Right? So here's a question. Maybe we can elevate the conversation a little bit by getting some feedback. And just out of curiosity, just so you know, your camera is not focusing, so you're all blurry. How do you pick out a random variable in a trace? In the higher order context?
I don't think I understand the question. What do you mean by pick out?
So in this context, we're doing Metropolis Hastings in the space of traces. So we're doing evaluation-based Metropolis Hastings. So you've done graphical model-based Metropolis Hastings, but not evaluation-based Metropolis Hastings. I'm not going to make you do evaluation-based Metropolis Hastings. It's not going to be one of the homeworks. But you should think about what's going on. And this notation makes you feel comfortable and makes you feel happy because it's sort of, you can get the gist of what's going on, but I want to just go down just a little bit lower level. So X is a trace data structure, right? And what I'm saying is that you need to be able to pick one of the random variables in a trace. So how do you pick one of the random variables in a trace? How do you uniquely identify a random variable in the HOPPL context?
By its name.
What's its name?
Whatever the string that it comes up with is.
Addresses, yeah. So we've got it in the chat channel from Mia and Tony. So the address transformation gives you a unique name for a random variable, right? So when you're running lightweight, when you're implementing or running lightweight Metropolis Hastings, you would keep around a dict that maps from addresses, right, to random variables and their values and their log probabilities and anything else that you want to track. So you pick from this hash map uniformly amongst its keys, basically the addresses, right? And then in a distribution specific way, in other words, whatever the type of that distribution is, you can make a local proposal. So there's going to be some kernel, which is going to be, for instance, if you have a normally distributed quantity, you would just choose a multivariate normal with some small standard deviation and move just a little bit in that space. If this were a discrete distribution, you would choose a walk one up or walk down one down or something like that. Some local proposal, local to that address and that particular variable type. Okay. And then from that point forward, you just run the program forward. Just completely make a new trace. Right? This is a simpler version than what we talked about before, and you'll see what happens here. That's totally fine. So the single site update says sample from the prior, run the program forward. So in other words, basically what it's saying is this thing can simply ignore the previous value, right, and sample from the prior, right? That's totally fine. And then all we're saying is go into the trace, find an address, manipulate its value by regenerating it, and continue the execution of the program until the end. Okay. All right. That's the proposal. The joint probability of the new trace, of course, has all of the X values plugged in. So in other words, you're actually, when I'm writing this here, you're actually reevaluating the likelihood of the under the observes as well. So you have a slightly different value here, right? And of course, you can reverse this process now, right? In other words, given however long the new trace is, you can evaluate how probable it would be to pick the same address again, because you know that the address will be preserved from one trace to the next, right? So that different length will be m prime. And the probability of picking the same address out of the new trace is 1 over m prime instead of 1 over m, right? And then to generate the old trace, right? So to generate the old trace, you just run forward and generate the retained values in the old trace.
Can I ask a question here?
Yeah.
By address here, do you mean the sort of sequence of addresses, i.e. trace, or do you mean the address of a particular sample statement, if you know what my question is?
The latter. So the whole point of the addressing transformation is to provide you a unique identifier for a random variable. End of story.
So I don't know if this question makes sense, but does that mean like as we go along, as we travel through this trace, we need to always make sure we save the random variable's address? Is that like an extra step we need to do in this context?
Yeah. So when an evaluator for the lightweight Metropolis Hastings like in a lightweight Metropolis Hastings evaluator computes a side effect at the sample statements as well, which is it has to keep track of the address, the type, and the value, and for efficient implementations, the log probability of that sample under that execution trace, right? So a lightweight Metropolis Hastings evaluator will override both sample and observe. Of course, it's going to wrap the whole thing in a Metropolis Hastings loop, but it's going to override both sample and observe, and it's going to use the addresses that are provided at runtime to identify the random variables uniquely. Right. So you've started to see the address transformations that we've provided to you. You know, this year, we're not going to do lightweight Metropolis Hastings. We'll do sequential Monte Carlo because it's closer to deep learning and blah, 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 blah. But sort of the workhorse of probabilistic programming has been lightweight Metropolis Hastings. In order to get lightweight Metropolis Hastings to work, you have to have the addresses. In order to have addresses, you need to pass them along runtime like we did. And then you need to override sample and observe statements to keep track of these. And of course, this object then, if we've managed to develop a vocabulary that we can talk to each other about this stuff relatively efficiently, should be something that you could imagine how to compute on a pass and then a subsequent pass through the program. So the first pass through the program, would allow you to compute this, because that's going to sum the log probs of the observes and sample statements, right? Okay. And of course, it should be relatively straightforward to see this as well. There is some set of addresses here where if you put the addresses in here, oh my God, the notation is it gets completely out of control. Clearly, some of these expressions, some of these log probabilities, or some of these probabilities are in this. So if you remember, I talked about reuse versus resample versus whatever when we were talking about lightweight metropolizations before. I did some simplifications. This is not simplified. This just shows you exactly what's going on. It's as straightforward as possible, right? Then you can be efficient on top of this by recognizing that, in fact, actually, here, there's a bunch of these in here, right? And in fact, wherever the resample site is, these are all of the addresses that follow it in the trace, right? They're the exact same. And of course, when you run a second time, right, you certainly can track all of these. You would track all of these, right? And you would, when generating this probability, right? And the way you would tell whether or not these two overlap or are allowed to overlap is by comparing their addresses. So if you return to the same address during the subsequent execution of the program, you may wish to, and it's entirely up to you, reuse the old value and continue from there, or regenerate a value. So there's a degree of freedom here as to which of these terms cancel and which of these terms cancel with these, so on and so forth. Make sense? Please ask questions.
So if this is your sort of, you sort of sample an address, restart from that address.
How do you restart from that address?
Well,
you can't restart from that address. You have to replay. So relative to those of you who may end up doing something in Pyro, which I suspect will be relatively few of you for a final project, because I hope that you get into the research bit just a little bit once we get to some of the more the next few topics and open your eyes to what we're talking about. You have to replay the trace. So like Pyro has a thing called poutine, which allows you to replay a trace. In other words, you run the program with the values that are in your dictionary up till that point.
So I'm sorry, then maybe I didn't understand the answer to my previous question of like,
yeah, sorry,
a sample in this case.
I stepped on you while you were asking your question, so that's totally fair. Yeah.
A sample in this case should then imply, sorry, an address in this case should then imply a sequence of addresses belonging to each of the individual sample and observe statements, right? Because that's sort of the state that your program is in. Or am I misunderstanding this?
No. So if you look at the address transformation, and in particular the push address function, the push address gives you the stack frame effectively. So the address itself already identifies where. So the address is a unique identifier for a random variable. It gives you the stack frame.
Yeah. Okay. Yeah. Good. We're on the same page. Sorry.
Okay.
I just wanted to ask, because I didn't understand part of your response earlier. What do you mean by we need to override sample and observe?
Sorry, when I say override, I mean that you would, in an LMH interpreter, the base cases for sample and observe would have to consume a state which you also thread through the interpreter. And that state would consist of a map of address to values at the very minimum. And in fact, you would need a previous map and a current map, or whatever, or a current map and a proposal map. And then you need to be able to do this arithmetic at the end in order to compute an acceptance ratio. And then you just rerun your interpreter over. You pick an address, rerun your interpreter, mess around with a bunch of stuff, compute an acceptance ratio, update the states, rerun your interpreter, pick a new address, rerun your interpreter, so on and so forth. So if you remember when we talked about this problem of, and this is a really interesting algorithm, actually, when we talked about the problem in graphical model Metropolis Hastings of making a joint proposal, right? There's no way in large graphical models to make a joint proposal of all of the random variables at one time in such a way that you have effectively a non-zero acceptance probability, right? Hopefully that's clear to all of you, right? So what we said is, okay, one way to do this is to write a Gibbs sampler and then make joint proposals for subsets of the variables. And if you make those subsets such that they're exactly one variable, then generally speaking, you can get a reasonable acceptance rate on the one variable. But the overall acceptance rate or the overall ability for the Markov chain to explode the space is not going to be very good. So you have this tension between wanting to make the biggest block change you can so that you move as efficiently as possible in space, but not actually being able to do that. So this kind of kernel is actually really, really interesting, and the people who came up with it in the first place are pretty smart for having done so, because what happens is you make one change to the program state, and in fact, there is a joint proposal which may impact very, very large numbers of the random variables in the program coherently. Right? So you can think of this as a really neat way, a general purpose way of building a fairly complex proposal mechanisms for Metropolis Hastings, right? Automatically. That make sense?
Can I ask a question
Please.
too?
Yeah.
This is not really related to what we've been talking about, but mostly because my brain blocked out all of last week. What?
That's bad. Okay.
What is gamma?
Gamma is an unnormalized probability distribution.
An unnormalized probability distribution. Is it is there a specific type? Is it like a prior distribution, or it's just a distribution? Okay, thank you.
It's the standard. Whenever you see this, like whenever you see one thing that I'm hoping will come out of having taken this class is that at the very minimum, when you see papers that do sampling and they talk about Metropolis Hastings, they're just going to write down acceptance ratios, right? And almost always this thing and this thing are some joint distribution, and they'll always refer to it as a target, right? But it's always a joint distribution, and what they're really targeting is a posterior distribution. That's it. Or there's some energy-based model in which you have an energy, but you can't compute the partition function, so you just write down the energy, right?
Is there why are we multiplying by m and m prime? I don't see like an intuitive.
Doesn't have to be intuitive. There's the proposal.
Okay.
So this actually, the original lightweight Metropolis Hastings paper, believe it or not, had a major error in it, and this was sort of at the beginning of my Prob Prog career, which is, why is there an M, right? And the M is, how do you construct the proposal? The proposal is pick one of the addresses from the trace, that's this term, right? And then modify that one, and then all subsequent ones, right? So if you'll notice,
I missed the 1 over m. I think that's why.
Yeah. So the m goes on top, and then the Hastings ratio means that there's an m prime on the bottom, right? Which is just the length of the other trace, right?
We need to look at the definition again.
This one.
Yeah. Okay.
So pick one of the random variables, apply a local kernel to that random variable. This is the, Metropolis within Gibbs kind of idea. You just like fiddle around with one random variable and then recompute the rest of the trace. Okay. And what this slide says is you can even make a simpler choice. You don't have to have this special proposal distribution. You can just sample from the prior here. And that means that this is not up. There's no +1 here and there's no +1 here. And there's no k's in this ratio. They just go away. So you just say, pick the variable, resample it from the prior, running the program forward, and recompute the rest of recompute the rest of the trace. Okay.
So we always take out one random variable at a time. Is that correct?
So this one identifies one random variable per address, messes around with it, and recomputes the remainder of the trace. Yeah.
And so when I'm thinking back to like Gibbs sampling, we would just accept or reject this one random variable. But now, I don't know if I understood everything before, but it sounds like there's other stuff that happens. Like you said, there's like some kind of side effects or like.
Yeah, because you can't, there is no way to compute the conditional distribution of one variable in a trace-based program. It's not possible, right? Because you can't define the graphical model, and you can't then like run Markov blanket determining programs on the graphical model, which doesn't exist, right? So there's no way to derive the conditional distribution for an individual variable, which means you can't run Gibbs, right? So this is Metropolis Hastings, where the proposal is this thing. So it's proposing to go from one state in a Markov chain, whose equilibrium distribution is the posterior distribution, and the Markov chain consists of an entire trace. And the way we're going to go from one trace to the next is pick one location along the trace, modify its value. But when you modify its value, think you're in the middle of a program execution. The program could branch 6 ways to Sunday, conditioned on the new value you choose here. So you choose a new value here, you keep running your evaluator. It's going to go somewhere else. It's going to produce a different trace. So instead of changing one value, we're identifying one value, and we're using that to say the entire rest of the computation can change. And this is the entire rest of the computation. And this gets close to Barron's comment about, pick an address and run the rest of the program. And this gets closer to continuation, so we'll see that in just a second. So again, bearing in mind that this is, stepping out of the program, lightweight Metropolis Hastings says, okay, run the program. The first time, just run it, right? You're going to get some, I guess we should use here X, sorry. I don't know why these are Zs. Went back and forth for a while. So you're going to get a sample of the latent variables in the program, fine. In the subsequent run, you're going to pick some address. In this particular case, it's this particular sample location. And you're going to rerun the program and then choose to keep this trace or keep this trace or this trace. And the one repeat here is meant to say that for whatever reason, this trace was rejected via the Metropolis Hastings procedure. In other words, we did a proposal, we ran it out, we computed the acceptance ratio, and we rejected it, right? The next time we pick a different address. So this would be at alpha 3, alpha 1, something like that. And what we do is we run the program looking up the values of all the random variables that we generated before in our dictionary. We choose a new value here, we go on, and we either accept or reject the sample at the end. Maybe I should make you do lightweight Metropolis Hastings. Everybody's not paying attention because I told you don't have to do it. So maybe I'll change the homework now. Barron would like that. So that's lightweight Metropolis Hastings.
So It skips the numbering on number 2 because 2 was rejected and 1 was kept instead.
Yes.
But the second line actually represents 2.
Yeah, so this would be the second trace that's run, but then it's rejected. Yeah.
Okay.
So there are a bunch of lightweight Metropolis Hastings variants, which are pretty cool. And there are some papers that you could go off and read if you wanted to. So the original lightweight Metropolis Hastings paper, which again originally had an error in it, a rather bad one, is this right here. And it is exactly as I just described. Berend actually suggested the second most advanced version, which is if you have your program written in continuation passing style, then at every sample and observe statement, basically at every address, you also have a continuation available to you, a continuation function. So when you do Metropolis Hastings, now you can be really, really freaking fast, actually. Because when you look up the address, you also have a function that represents the rest of the computation. So you just look up the address and call the rest of the computation. And that's what Anglican and Web people did. And then there's a crazy version, which I probably 75% understand, which is C3 lightweight incrementalized MCMC for probabilistic programs using continuation and call side caching. Basically, what it does is it looks up a values. In other words, this is computation that doesn't need to be redone. Okay, so if you can save computation, that's really good. And if you can prove that your trace will return and never modify any random variable in the future, that's what this paper is about. Just reuse the entire trace from that point forward.
Does that just mean that the rest of the program is deterministic, or that there are no more observes in there, or like?
No, it means that you'll stay on the same control flow path. If you stay on the same control flow path, and you there's like two conditions. You have to stay on the same control flow path, and the values of observed quantities or the values of the link functions can't go outside the domain of the allowable values for distribution types. Those are the two requirements. So in other words, so long as you're on the same control flow path, you may, if you can prove that you're on the same control flow path, then you are 100%, almost 100% guaranteed that you can reuse the sample values. The only way that you wouldn't be able to is if for some reason, your choice of random variable leads to a standard deviation that's below 0 or something like that. Mm-hmm. But that would still be okay even. You'd just end up getting a rejection. So really all this is about is staying on the same control flow path. So you have to do a source code analysis in order to make sure that you're on the same. If you can prove that in the continuation function you will stay on the same control flow path, then you reuse.
Yeah, okay.
So
I also ask a quick question.
Oh.
You can go ahead first.
So in the not this last version, generally the program is path dependent, and then in this last one it's saying if you have small sections that are path independent, then you can kind of
go away and then come back in.
And
exactly.
Jump to the next path dependent section.
Yeah.
Okay.
Can't you still do the second method without using the continuation passing approach? Like it's kind of dumb, but you can preemptively decide around what point of your trace to resample from. And when you're at that point, you can just make a copy of the current process and not run it, right?
I think we spent, Baron, what do you think? We spent 3.5 hours arguing about this today, something like that.
That's about right.
So
Actually, it was 4.5.
Was it 4.5? Okay, yeah. The answer is it would be extremely not obvious how to do that in an interpreted environment. In a compiled environment with POSIX fork, maybe, but in an interpreted environment, very, very hard to do.
Okay.
Maybe change this to, if you know how to do it, then
please
then
tell
you
us.
can come and help us out.
Oh yeah. Okay. Yeah. Let's take our little break now. Chillax today. 4:25. We'll take a full 5 minutes today. Welcome back. Okay, so on to sequential Monte Carlo. Just we've done this in general, but the idea here is to think about sequential Monte Carlo in the probabilistic programming context. Here we're going to switch notation from before just ever so slightly. You probably won't even notice the difference, but instead what we're going to say now is that we're going to associate a subset of the variables in a trace with each observation. So x tilde here is just going to mean x tilde 1 will be all the random variables generated in a trace up to the first observation. And then x tilde 2 will be all of the random variables generated after x tilde 1 en route to evaluating observation y2. And now the same trace as before, just tilde, so we have a different set of indices on it. Now we have x tilde 1 to n, that's the entire trace. And here's Emma's favorite gamma, which is the unnormalized distribution that we're targeting. But note also that we have a sequence of targets now, right? In the canonical state space modeling sequential Monte Carlo sense. Okay? In other words, we are interested in first the posterior distribution of all of these latent variables given this latent variable, and then the posterior distribution of all of these latent variables given these observations, and so on and so forth. So it's very easy to squint at sequential Monte Carlo and see what's happening as something different than that, but what's actually happening is the sequence of distributions that we target in sequential Monte Carlo in the probabilistic programming context is this particular sequence, which is ever so slightly different to the standard state space modeling context, but only marginally so.
Sorry, just to be completely, make everything completely clear here. The difference is that in the Prob Prog context, you can also have dependencies on further than, or on any of the previous variables, rather than only on the previous one.
That's correct. Yeah. So and moreover, if you think about what the transition function for p of x2 is given x1, it's a little bit funny, right? Because this contains this, right? So it's even kind of a little bit difficult to write it down in mathematical notation, because you have to write it down that, x2, this is, whatever, x2 is distributed from p of x2 given x1. And you can either have this defined, or you can say that x1 is distributed Dirac, x1 here. In other words, basically, the whole point is you have x1 here. That is constant, and you're just growing the environment. x2 is here, and it's random. But the sequence of state that you're tracking grows, right? Because you're actually keeping track of the entire interpreter state. And even this, as you know, and as all of you will know when you implement sequential Monte Carlo, is also slightly alive, but not really. Actually, I take it back. This is accurate. It's the entire evaluation context of the program. The interpreter state doesn't play into this. So this is notationally fine. Okay. Cool. All right. So the actual thing that we're after is the normalization of this, and of course this hides the y's, right? So this is just integrating over all of the x's. This is just integrating over all of the dx 1 to n, right? Of gamma in x 1 to n. Okay. Fine. And how do we do this? Okay, so we want samples from pi in x twiddle 1 to n. So we want samples from the nth. We want samples from the nth iterate of the algorithm, where the nth iterate is some checkpoint or observe. And from the lecture that we had before, we know that this is proportional to the likelihood, or the observe, the nth observe, times the probability of transitioning, times the distribution up to n-1 of the states up to n-1. Okay, so we did that literally last lecture, the lecture before that. The recursion occurs when you see that if we have a particle approximation to this, so just to put your thinking cap on for a second, how do we get a particle approximation to this up to the first observed statement?
I realized that I wasn't on mute. Sorry.
No, you shouldn't answer this one. I want one of the lovely, bright participants in the class.
What is a particle approximation?
That's what we talked about for the entire last 2 lectures. So these are the...
That's what was blocked from my brain. I'll go back and read them.
Particles are samples. So we have let's presume that we have samples from this distribution. Okay, so if I go back to here, that distribution is this guy. It's technically the posterior distribution of that. So if you just had that and you just get rid of all of this, how would you get that?
Now I'm confused again, because you said we had that, but then you asked how we get it.
We assume that we have it. So I'm saying that, like, in the derivation of the recursion, we assume that we have it, right? And I'm now saying start at the beginning and give me P of X
Okay.
not in, but the first one.
Could you do like a partial importance weighting? Just run it up till they're
Boom is all over it. It's lovely. Yeah, you just run importance sampling up to the you run to the first observe. You get the likelihood. You have weights at the first observe, and now I have a particle approximation to the to this. So you just run importance sampling. Yeah. Okay. So that sets the base case of the recursion. You literally start the program. We're going to say k is the number of particles. You start the program k times, and you get an importance weight for each of those particles. Then you normalize the importance weights, and if you want, you can resample. Now you have a particle approximation, and if you resample, the weights are 1 over k. If you normalize the weights, which you need to do, then the weights might not be 1 over k. That's totally fine. But we have weighted atoms, right? So I could replace this with dot if that makes everybody feel happier. You have a discrete approximation to the target, the n-1th target. Just keep in your head that you have an approximation up to the first one. That's totally fine. Now we're going to go to the second one, right? So how do we proceed to, n equals 2, or in this particular case, n, right? So for each particle, oh my goodness. For each particle, we have k equals 4 here. And we have Dirac x1 to n-1, 1 here, and Dirac x1 to n-1, 2 here, and Dirac x1 to n-1, 3 here, and Dirac 4 x1 to n-1. And there's some weights associated with these. But let's just assume that they're 1 over k. So 1 over k, 1 over k, 1 over k, 1 over k. Fine. The first thing that we do is we have to pick which particle to continue. The first thing that we're going to do is we're going to sample from this discrete distribution. And this one will pick this, 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 which means that these are not continued. That's this ancestor thing. These are called ancestor indices. Okay, so you pick some ancestors to continue. Right? Then what do? Next thing you do is you run the program forward. That's going to evaluate all the sample statements in this next block. Okay. And you deterministically construct the new particle. So these are almost these new particles. Pretty close. But we need importance weights for them. Reveals. Hopefully you can see the importance weights. The importance weights are just the likelihoods. I should use a different color. Wrong color. I'll do it with this color. The importance weights are the likelihoods. They're the observed statements. And once you get here and have generated the unnormalized weights, you generate normalized weights by normalizing the weights. And for Greg, who's been, who's on a tear thinking about sequential Monte Carlo already, that's great. It's these things in particular, it's the product of these that you multiply together to get the marginal probability estimate. The product over all observes of the sum of the unnormalized weights. Okay. So there you go. There's the entire sequential Monte Carlo algorithm for higher order probabilistic programming on one slide. This is homework 6, so you better ask questions. It's also an incredibly valuable algorithm to know about in general for basically any sort of modern AI application, so on and so forth.
Can I ask a question about it?
Yeah.
So one of the things that is sort of tricky with I guess importance sampling is that, you know, if your prior is not very good, then you're never going to get any high likelihoods, and it always sucks. This does a lot better because you throw away those samples that are not going to have a high likelihood anyway, but you still sort of run into hand wavy.
No. It's the reason why I did the little head bob is that it's not entirely clear that you throw away the right stuff, right? Mm-hmm. So they may have in the reinforcement learning kind of context, you may have to go through low probability regions to get to high final probability, or low reward to get to high final reward.
You're right? Throwing away the stuff that hasn't seen a lot of evidence for up until that point. Maybe evidence is a poor choice of words here because that means something else in this context too. But
it did. Yes.
But so okay, so that's an issue. And the second thing is that if the sort of prior samples that you're doing in between your observed statements don't get you in the right direction, then you're still kind of in a bad spot. Right?
Yes, but the reality is there are sort of, this actually segues nicely into the remainder of the course, which we'll start getting to pretty soon, which is like, well, if your model is bad, then inference in that model is going to be hard because the model isn't going to explain your data well, right? If your model is really, really expressive, it may be that inference is still hard, right? In which case you might have to do something smarter than proposing from the prior. So there's at least two levels of complication here, right? One is your model good? If your model's good, then sampling from the prior is going to put you in the right direction all the time because your model's good. If your model's not good, or if it's not great, then you probably need to add some proposal distributions in here, right? And those proposal distributions would need to be learned from data. Or you need to learn your model from data, or you need to learn both from data. And that's where we're going to go. Right?
So to make that like absolutely explicit, learning these proposal distributions is something that we're going to do, because that sounds like a really obvious thing to work on.
That would be homework 7 if we decide to do homework 7.
Gotcha.
For important sampling, we wouldn't do it in the sequential Monte Carlo case, but for important sampling, which they're kind of the same. That's an advanced question. Either that was a suppressed yawn, Mia, or you were working up the courage to pop off with a good one.
It was a thinking sigh.
Thinking sigh. Okay.
I guess I do have a question though, just on the sort of implementation level. This is what the message passing stuff in the book, like actually doing the stopping and starting of executions. That's what that is about, right?
That's a large part about what it's about. Yeah. It's what's hidden here, and what you really can't get until you work through the struggle of trying to implement sequential Monte Carlo. So there's, I guess, a couple of things. One is if you implement sequential Monte Carlo for this view of models, then you have an absolutely generic implementation of sequential Monte Carlo, which is useful for inference in any nonlinear dynamical state space model. It's hugely valuable. Okay, so like you're going to get something out of this no matter what, so that you know how to implement sequential Monte Carlo in a really wildly general case that even people who do sequential Monte Carlo research don't really understand, because they don't think about like the co-evolution of program evaluation. They think about state space models, and they are different. But I would say that the sort of the intellectual gotchas when thinking about how to implement this in a practical sense, and this is something that actually we're running a running a sprint right now to try to stay ahead of you on in the homeworks as well, is that when you do this operation, in other words, when you continue the execution of the program, it may be that these variables, these ancestor indices, are the same for multiple continuations. In other words, if I very explicitly made it the case, I drew these little green lines, right, that said, for instance, all three of these subsequent particles come from the same mother particle, so to speak, which means that the evaluator's environment must be a pure data structure. Otherwise, you can go in and screw around with the environment here and here and here and have them collide in horrific ways. Right?
I should have asked this a while ago. What is a pure data structure?
A pure data structure or an immutable data structure is one in which there are no modifications allowed to the data structure. No in-place modifications.
How is that enforced?
How is that enforced?
Yeah.
By making the how is it enforced? By making an interface guarantee. You can't enforce it, right? Like there's no way to enforce it except to say that if I give you an object whose contract is when you call plus, or when you call add, or when you have a hash map and you add an element, that add operation returns an entirely new, or what you believe to be an entirely new data structure. Underneath, you can do an implementation. So like conceptually, you can conceptualize of it as pure data structures always return copies of the, this is why I've talked about deep copying, right? Pure data structures, you can think of it as returning a beautiful deep copy automatically. But the way pure data structures are implemented is that behind the covers, they're actually just providing you a view of a very advanced data structure that uses a whole bunch of trees in a nice way to host your hash map on top of a data structure that you don't have to understand. You can think of it as being immutable because the interface is immutable. Underneath, there's mutation happening, but it's happening in a way that makes your interface to your particular data structures seem like you're getting copies. So you can declare one map, then assign it to another variable, make modifications to the other variable. Your original reference will stay unmodified.
Thanks.
The other thing that's somewhat complicated, and this is what we spent some time worrying about today, is that when you're implementing the evaluator, it is very difficult to jump back into how to say this the right way. You need your evaluator to be reentrant. And the long story short, the way we're going to solve this for you is reentrant. In other words, you can re-enter it and continue. The way we're going to solve this is that we are actually going to give you one more source code transformation on top of all the crazy transformations that you've seen so far, and this will be the continuation passing style transformation. And you'll have access to an explicit continuation so that you can make your interpreter reentrant for free, basically.
I have a question about computing weights.
Yep.
So at the nth step, when we compute the weights,
Yep.
do we also add the weights from the previous steps?
It depends on whether or not you resample. If you resample, then there are no weights from the previous steps.
Okay.
Right. And if you don't resample, then indeed you accumulate weights just as if you were important sampling. Because really all we're doing, sequential Monte Carlo or sequential importance resampling is simply sequential importance sampling with a resampling step thrown in to improve computational efficiency.
Okay, I see.
So you're important sample, pause, resample, go. That's what's happening. And you may choose to you need not do a resampling step at every at every checkpoint or observe. Right? You shouldn't do so. In fact, you should only do so when your effective sample size falls below a certain threshold. Okay. Cool. Different diagram, same idea. So now we're going to, if you're really adventurous, what we're really talking about are now, we also get to be parallel now. So you can do this with important sampling. Obviously, important sampling, you can run all of your evaluators in parallel, right? But what's happening here is you're going to have some number of threads or processes or evaluators running, and all of these need to hit an observe breakpoint. And here I talked about addresses, again, being required for sequential Monte Carlo. You need to only break on observes that have the same address. So you need to do an address check at the observe. There will be some weights that are computed as side effects. These are the size of these balls, right? And according to those weights, ancestors for each of the daughter particles will be chosen, meaning that some threads or processes or evaluations will not continue, and some will continue in multiplicity. And the evaluator will continue. So intuitively, what's happening is you run the program multiple times, then you wait at some observed checkpoint, you wait according to the observes, and then you continue preferentially based on the weights that were computed. Clear enough? Okay. We know some fun facts. We talked about them the other day. One of them is you get a marginal probability estimate out. That's pretty cool. And we could talk about why that's cool, and it's cool in a number of ways. One of which is this is useful for iterating sequential Monte Carlo, like we talked about, because we can use this as an unbiased estimate of the marginal probability estimate for a Metropolis Hastings sample that allows us to iterate sequential Monte Carlo, so we don't have to actually just stop after n particles or k particles. It's also useful for model learning because as it turns out, this is also a lower bound on the marginal probability, which we'll maybe get to. Yeah, so computing this is a good idea for future references. There's some rules of thumb. You should always run as many particles as you can, and unfortunately, you can't always run as many as you need to. So there's a bunch of different algorithms, one of which we just talked about there, which is basically the important sampling version of iterated sequential Monte Carlo. There's a paper, particle Markov chain Monte Carlo methods, which you should actually be able to read now, which is cool. And in it, there are a bunch of iterable sequential Monte Carlo algorithms. PIMH, particle independent Metropolis Hastings, which is basically what I just described, where you run sequential Monte Carlo, or I described last lecture. You run sequential Monte Carlo, compute the normalization constant, run sequential Monte Carlo again, compute the normalization constant, and accept or reject entire particle sets. Okay. And this diagram here, just to be clear, these are the orange ones are the particles that do not continue. The dark lines here are the likelihoods. The size of the balls are the weights. And then you see what's happening. So these are continuations that end at the next resampling, and so on and so forth. And you have a consistent size set of here six particles. Okay. And every sweep can be different. So your sequential Monte Carlo algorithm ideally will not just return K particles, but will return a stream of particles which is emitted in K chunks that you compute which of this versus this comes out is the next K chunk using the Metropolis Hastings rule that we talked about last time. Okay. So that's what we did last time. So we have sweeps along this row. These are the marginal probability estimates that come out. Each sweep of SMC computes the marginal probability estimate. PIMH, particle independent Metropolis Hastings, accepts an entire new particle set with probability equal to min of the ratio between the marginal probability estimate of the new proposed sweep versus the old sweep. And you can use all the particles that come out. And just these are the last weights from each of the sweeps, so you don't do a final renormalization step. This is if you do a final renormalization step, this just goes away and it's just 1 over K times S. And Q here is your test function. Okay. So now we're up to 2014. Yay, we've made it. Okay. And you can go much, much further with this. And there are some really, really cool algorithms that still haven't been exploited in, say, for instance, reinforcement learning land or something like that. Interacting particle Markov chain Monte Carlo, you should read in a reading group sometime, is a distributed parallel particle Markov chain Monte Carlo algorithm. And here there's a, it's cool. There's a crazy algorithm that runs sequential Monte Carlo itself in parallel. 1, 2, 3, 4, 5, 6, 7, I guess 7 parallel chains in this particular case. Every one of these is a sequential Monte Carlo algorithm. And the size of these dots corresponds to I guess there are 8, excuse me, that just didn't see this one. It corresponds to the marginal probability estimate of that particular sequential Monte Carlo chain. And what you see here are sequences of either running conditional sequential Monte Carlo, which is in blue, or unconditional sequential Monte Carlo, which is in orange. Okay. I haven't talked at all about conditional sequential Monte Carlo, but particle Gibbs is a very particular algorithm, which is basically a variant of particle independent Metropolis Hastings, where you retain one trace. And you run a conditional sequential Monte Carlo algorithm while retaining one trace. And it turns out that when you do that, the acceptance ratio via a very, very complicated and painful argument is 1. Okay. So you can run sequential Monte Carlo over and over and over again, provided that you keep a trace around. And that actually really is 2014. Okay. These are conditional sequential Monte Carlo traces. These are unconditional sequential Monte Carlo traces. And which becomes or ends being a sequential Monte Carlo, a conditional sequential Monte Carlo trace is computed via an interesting algorithm, which you can read about, which involves a Gibbs update on which ones are and are not conditional sequential Monte Carlo. The nice thing, I don't think this is going to run. That stinks. The nice thing is that running, say, for instance, IPM-CMC gives you actually very good marginal probability estimates even at the beginning of the trace. So we talked about particle degeneracy and the fact that the posterior distribution is unequally good for variables late in the trace versus early in the trace. They're still unequally good, but it's massively improved by algorithmic improvements to sequential Monte Carlo, like IPM-CMC. So where are we? HOPPL programs, we know we can't unroll into graphical models in general. So we can only evaluate the joint probability of a trace. So the solution, one solution, particularly the SMC solution, is to treat HOPPL programs like a state space model where the state is the state of the interpreter or virtual machine or process. Okay? And that's really the homework 6 thinking that I wanted to get into your head. We've talked about the fact that sample and observer statement treatment in HOPPLs are semantically equivalent to the HOPPL ones on purpose. This is stuff left over for something else, so we shouldn't talk about this, except for the lots of details pushed under the carpet, but you'll uncover some of the details when you do sequential Monte Carlo in homework 6. So I think that's it. Thank you, and I'll take questions.
Is there any benefit in sequential Monte Carlo, just the simple version that we're doing? Is there any benefit to doing more parallel evaluations than you have hardware threads? Do you improve your output by having more of them in that way?
If this is going to require probably a back and forth in order to get to the final thing, and I'm wondering whether or not you actually have a systems reason for asking this question. Sequential Monte Carlo is exact if you have an infinite number of particles. So the more particles you can run, the better. Period. So relative to like the number of threads on a machine or something like that, that's one of the reasons for the IPM-CMC algorithm actually. So there is a maximum thread count, and there's memory considerations on a single machine. If you actually want to run distributed sequential Monte Carlo, this algorithm is the algorithm that's designed to do this, and that's how we got to very, very large scale inference results using sequential Monte Carlo. So basically, literally, this is distributed parallel sequential Monte Carlo, right? So yes, there are reasons why you want to run more. There are reasons why you want to iterate sequential Monte Carlo, and this is one such algorithm. Although there's others that are, envisionable. More questions?
I have a question about the resampling step.
Yep.
So is there like intuition, like why it works and why it doesn't mess up anything statistically? Because we are like sampling, we are resampling from approximation of posterior up to the current point. Or like, should I just look at the proof and yeah?
I think if you want, you need to look. So like, yes, really you have to look at the proof to really understand why the marginal probability estimate is unbiased and yada yada yada, and what the intuition is that expectations taken against the weighted particle set versus the unweighted particle set are the same.
Okay.
right? If you actually, like write down the expectation, you pass the expectation in, it doesn't matter whether the particle set is weighted or unweighted. The expected, the Monte Carlo estimate, the expected Monte Carlo estimate is the same. Doesn't matter if there are weights or not.
All right.
Right.
Makes sense.
So if you can save computation and direct your computational resource to higher weighted particles, that's a good thing. So again, like the whether or not this works though, like in practice, is very much goes hand in hand with whether or not you get information along the way that is well correlated with the final likelihood.
Okay.
Right. And this will become a little bit more obvious when we talk about reinforcement learning as inference, which will come relatively soon.
Okay. Yeah, I have one more question about the homework, but yeah, maybe someone has more questions on topic.
I think I want to refine my previous question and ask, so if we're running on a single computer,
Yep.
just this basic version, and we
Yep.
have, X hardware threads, obviously we can run 8 steps in parallel, or we could run 16 and it would take twice as long because it'll go in sequence. But then
I say, okay, so
thinking-
you're saying there's actually, you're talking about like there's actual concurrency on the machine. Is
Right.
it worth running? Is it worth running more particles than there are
Right,
threads in the machine?
because you could run twice as many particles, but then you get half as many resamples, hand wave. And then, so is there any sort of, is that just a hyperparameter trying to figure out what the correct ratio for those things are for your application?
So again, it kind of boils down to whether or not you have sort of real-time requirements, right? If you have real-time requirements, then you should, no matter what, run as many particles as you can. And so what if if there's actually not as many actual compute threads as there are particles, because you can loop over them. If your hyperparameter or your optimization is variance over compute time or something like that, then there's a hard decision to make about how many particles you run versus how many times you iterate sequential Monte Carlo, because you're going to get into degeneracy no matter what, unless you have a huge number of particles, in which case you probably want to iterate sequential Monte Carlo itself, right? So then there's a sweet spot that's a little bit difficult to characterize a priori. And just for the fun of it, if you're into parallel computation for whatever geeky reason, I am, then you should be aware that the number one computational bottleneck in sequential Monte Carlo is not having a thread, run these local things so often. You can have as many, we're good at that, right? What we're not good at is thread synchronization. So if you think about it, the resample step is a thread synchronization, right? So you are going to lose processor efficiency big time if you have to actually wait and synchronize. So we also, with Arno, wrote a paper called the particle cascade. No, that's not what we called it. That's what it was called. But we wrote an asynchronous anytime sequential Monte Carlo. That's what it's called, which throws away the need to make barrier synchronizations. And that on a multiprocessor system on a single multiprocessor system is a very, very good way to get very high particle throughput.
So does that sort of mean that you have one particle. If it arrives, there are no other particles yet. It just keeps going. And if the second one comes in, then it either decides to continue with the first or with itself, something like that.
The rough idea is that you run the first particle through the system, and then you start. I like thinking about it in terms of single particles. We talked about it in terms of sets of particles, but single particles work just fine. Basically, you compare your weight to an average weight at every checkpoint, and then continue yourself multiple times or not. Relative, given how, or not even continue, depending on how you are doing relative to the average weight at that particular checkpoint. So you can just run, totally asynchronously, provided that you have a barrier for computing an average weight at every checkpoint. So there's one number maintained for every observed statement, and you just shoot particles through as fast as you can. Which is pretty cool. And has not been exploited by the reinforcement learning community, which drives me nuts, but yeah. Anything else? All right. Do download or repull Daphne. Christian has worked out all of the lingering bugs. So, thanks all.